Okay, so now resuming where we left off. We last talked about how we can calculate HP and HT, basically the hash values for P and T within theta of M time. Then we drew this function over here for it. And so, but remember, let me just grab my pencil. So remember that we take theta of M to calculate the first HT value for the first window. But for subsequent HT values for later windows, we only take either big O of 1 or the more precise theta of 1 in linear time. And this algo is in the next slide. Let's move on to the next slide. Actually, before that, let me just duplicate some of the slides. Jeez. Okay, so now we are doing the code to calculate the subsequent EST values. In theta of M time after taking theta of M time to calculate the first HT value. Yeah, just draw a long line here. Let's box. And this is the. Remember that this is without any hashing. Okay. But for the code with hashing, we'll use this. With hashing and without buffer also. Okay, let me just fix the indentation here. Okay, so this second paragraph of code here is what we want. Okay, so remember for I is the index where our current window is at. Our current, aka our old window is at. And remember that in this case, ht is the old ht value that we are going to use to get the new t value as you shift as we shift the window one place to the right. To the right, yeah, big R means right. And remember that in this case, D and over here, let me, let's correct this. There's some error here. Now it will be D to the power of n minus 1. Watch you. And then I'll just shift this. Rough a bit. Watch you. And then we also need to take note that this over here, and this is our most significant digit in our old window. And this over here is basically we have to plus q in this case because ht and the orders, which is this variable over here. Yeah, this variable over here. See where my mouse is at? Yeah, ht and orders were obtained after being modeled by q. So it's possible that ht is lesser than orders and we do not want that. So we plus q to ensure that ht plus q minus orders gives us a value greater than 0. So for example, if ht equals to 5 and orders equals to 7, and in this case, let's say q equals to 13, then 5 minus 7 mod 13 would give us negative 2. And we know that this only applies to C++, C or C++. Okay. Compared to traditional math, in math, okay, so in math, right, it should be 2 instead of negative 2. But in C or C++, is -2. Yeah, so we want to avoid negative values, which is why plus plus q so that we have the same result, but ensure that it is positive instead of negative. Yeah, actually, let me just write this part over here. So if ht plus q plus q or plus q minus orders mod q would give us 5 plus, in this case, q is 13 minus 7 mod q. So it's 11 mod 13. 11 mod 13, which is equals to 2, which is what we want. So this is why we just add a q over here. Yeah, it's one of the modulus rules in a sense. So let me see whether I wrote it down. Actually, I didn't really write it down, but I think it's quite intuitive in a sense. Because we're just adding q to it will change the absolute result per se. In this case, it will help us convert the sign from negative to positive, which is what we want. See whether I make any other errors first. Okay. This part over here, just a formatting issue. I think I have explained every part on this slide. Okay, but to make things clearer, we'll now go through an example. The next slide. So let me just write here. Example. Example from previous slide. Okay, let me just reinsert in the code here. And then I'll just select the pen again. And maybe I'll just make things clearer by saying that this code that you see over here is actually our old window t value without contribution from its MSD. Yeah, so remember in this case, orders is basically our most significant digit. And modding it by Q. So Let me just write it over here. So this is our most significant digit being modeled by Q. The most significant digit is the most significant digits multiplied by the, let me write it over here. Multiplied by the highest power for its place, and then afterwards modeling by Q, as you can see over here. Okay, so actually this is what X Z. Maybe it's more intuitive this way. Yeah, then I'll go back to the previous slide. Multiply by D. Okay, maybe this is more clear. Yeah, but asterisk and star both mean the same thing of multiply over here. Yeah, and just a reminder that we also have this over here. Yeah, we only need to calculate the M once, because we'll be reusing it multiple times later whenever we need to calculate or whenever we need to use the rehash function. Yeah, so we just pre-calculate it once. Okay, so now on to the actual example. Let's say if T is equal to 3, 6, 4, 1, 5, 2. And let's say M is equals to 5. Or HT is equals to 1. DM is equals to 4. Yeah, it makes sense because 3 is actually, in this case, equals to 30,000 for this window. So it's 3 times 10 to the power of 4. So DM is 4. And let's say we pick Q to be 7. So these are the parameters that we'll be using in the rehash function. And remember that I is the index of the window that we are currently at. So this over here, 36415 is the O window. And the O window has the hash value of 1. Yeah. And this over here is the new window. And since it's a new window, we will need to calculate its hash value. But in this case, when we want to find out its hash value, we'll do so using the rehash function instead. So we'll just feed in T 551. Yeah, so note that this I is this I over here. Okay. And this 5 is the value of M, which is the length of P, which is always fixed. And 1 over here is the HT value, is the HT value, is the OHT value. HA, the HT value of the previous window, which in this case is equals to 1. So actually, let's go through the function. So first we need to calculate those over here. See the underline it. Orders in this case would be equals to T of I. Okay, so it's T of I times dm, and we're gonna mod it by q. See, maybe I'll just erase this first. It's not that neat. Okay, so this is equals to 3, and dm in this case is 4. Yes, it's correct. dm is 4. And then modding it by q in this case is 7, which equals to 5. Okay, maybe I'll also explain how to get dm in this case. So this is how we calculate dm. You should either do it this way or the other way, which I mentioned earlier. Okay. Just have it as d, and then you just multiply 1 time less. So it's like this. But in the exam, it's more intuitive to think about it this way. Because if we want to get dm, so remember dm is the highest. Yeah, let me just say dm is the power involved with the most significant digit of the current window. Okay, so in this case, the window is 36415. Okay, so how I like to imagine it is, here is d is 10 to the power of 0, 10 to the power of 1, 2, 3. So this is 10 to the power of 4. So 3 actually has, so I imagine it as, this is the, yes, 4 zeros, so 3 times 10 to the power of 4 over here. Because remember, whenever we want to calculate the new value of the new window, remember this is 364,152. We minus 30,000. Yeah, correct. Minus 30,000. And then we plus, oh sorry, we need to multiply by 10. Okay, then we multiply it by 10. Yeah, because if we minus 30,000, we get 64152. And then we multiply it by 10 because we are shifting the window. Okay, then afterwards we plus 2. But this is the least significant digit, which is the same thing as actually, let me double check the previous slide. Yeah, so this is still the same core logic at where my mouse is. Minus G, the old test value. G, correct, okay. Got it. So t value is equals to, let me just put across here, 64152, which is correct. Okay, so back to okay, after we calculate orders removed. In this case, it will be HT is 1 plus Q. Q in this case is 7. Orders is calculated earlier is 5. And we mod Q, which is 7, which is equals to 3. And then we return orders removed and multiply it by 10. And we plus the least significant digit over here. Yeah, this is our least significant digit. So we plus 2. Mod 7. So 32 mod 7. 7 times 4 is 28. 32 minus 28 is 4. Okay. And now we'll be coming to the final part of this algorithm, which is the main code. So remember, the aim of the function, let me just shift it. And the aim of the function is to check if P appears in T, and if so, we provide the index where the first occurrence occurs. So let's say if, again, so let's say if it's ABC, P is ABC, and T is BABC, then DABC. Then the first occurrence is here, which is at index 1. So I is the index of the window that we're currently at. Yeah, so this is the index of the first occurrence. So that means our function code should return that. So I'm just going to paste the code here, and then we can break it down step by step. Then I'll just have to fix the indentation a bit. Way out this. Gee. Yeah, so this function assumes that we already pre-calculated the m before. Yeah, let me just get my mouse. Assume dm is pre-calculated before this function. Yeah. Yeah, and then this code over here. Oh wait, no, sorry, that was a mistake. My bad. This part over here is to calculate d of m which will be the power that we use to multiply with for the most significant digit. And let's see, actually, it makes sense that over here we calculate the hash value for the first window. Achieved. Let me just write the comments here. It's not exactly weird. Yeah, maybe I should do typing for now on, it's a lot faster. And then this is basically going through, similar to the logic for the naive algorithm here. For the while loop, we'll just check. We are only allowed to check from the first possible window all the way till the last possible window. So G only has this valid indexes from 0 to m minus m. And we increase it by 1 at a time. Then if the hash values are the same and both of them are equal strings, so remember how this equal string function works is, let's say we have in this case, let's say we have this over here ABC and B ABC over here. You check A against A, B against B, and C against C. So if all this match, then equal string will return true, and then we'll return J. And in this case, J is the index of the window that we're currently at. No, actually, in this case, this algorithm we use J instead of I. We are just changing the name. Then if J is lesser than m minus m, so basically this means, well, not at last window yet. As long as it's not the last window, it means that we can still rehash to obtain the hash value for the next window. Because if J is equals to m minus m, then that means we are at the last window. Therefore, there's no other next window for us to find the rehash value. And remember that these two are if statements. Yeah, but we can't execute them both together because the first if statement, if it's executed, will return. That means we'll immediately end the function. And remember that this hash function takes theta of 1. So this whole statement here takes theta of 1. And checking if HP is equals to HT is theta of 1. But this equal string function, worst case, it can take up to theta of m. Because remember, m is equals to length of n. So it's the length of p. So the worst case, in this case, we need to compare ABC against ABC. So there's 3 characters, which is m, which is the length of p. Which is why, in the worst case, this will take theta of m. And then, sorry, there's a maximum of m minus m plus 1. And we plus 1 because we start in this 0. So there's a maximum of m minus m plus 1 iterations. Yeah, so this is important when we want to find the time complexity later. Yeah, and as I explained earlier, the hash function is theta of n because if we Look at the earlier slides. Yeah, we can see that over here where my mouse is at is theta of m. So this over here is also theta of m. That's always what. This here is theta of m. Actually, let me note down the slide number. This was in slide 14. Let me just erase this part to make it neater. Yeah, I think now it's quite clear cut. And so, in case you are still confused as to why, let me find where's my mouse at. Okay. Let me just write here why e raised to 0 to j less than m minus m is because m minus m is the index of the last possible window. So let's say, remember P is ABC. So M equals to 3. And T is BABC, DABC. So N is the length of T, which is 8 in this case. So N minus M is 8 minus 3 is equals to 5. So index 5. So 0, 1, 2, 3, 4, 5. So this is index n minus m, which is the position of the last possible window, which is the last possible value that j can have, because the next value of j will point to b. And from b onwards, there's no point in comparing anymore because there's not enough characters left to match t. So no matter what, you'll definitely fail the comparison check. That's why once we are at the last possible window and the hash value doesn't match with HP, then we can safely conclude that P does not exist in T. Yeah, and then, so let's say J is here. Oops. Let's say J is here. J2 is 0, then J 1, 2, 3, 4, 5. Yeah, it's correct. Okay, so this algorithm is actually quite straightforward. It's just that it's quite tedious in a sense because there's many small functions here to take care of. Okay, so now we'll go through the final part. Yeah, I wouldn't say it's super important because the exam likely won't test this, but it's just the time complexity. Okay. Actually, yeah, easy off. Karp, I'll go. So it has to be better than, it is better than a naive solution. Yeah, because in this case, let's write it here. Worst case time complexity is equals to, let me see if I can just copy this. Yeah. The worst case time complexity is theta of m minus n plus 1 and the whole thing multiplied by n. So we'll look at the previous slide. Why is this the case? Okay, so to figure out, oops. So to figure out the length, this will take theta of m, this will take theta of n, and this calculating of dm takes theta of m. Yeah, correct. Because theta of m minus 1 is the same thing as theta of m. And theta of m, yeah, afterward you get the hang of it. Because theta of n, yeah. And this is the part, number of iterations, n minus m plus 1 iterations. So it's obvious that, okay, in this case, within it is also theta of m. Okay, so our worst case will assume that this equal string function over here will keep on being triggered every single time. And it will always take theta of n. That means we keep comparing until the last character, regardless of whether it matches or not. So there's really not enough space to write here. Goes to let me just see whether yes, number of iterations, then the worst case time complexity per iteration, which is this theta of m. Yeah, I can just delete this. So you just double check. Oh, here is theta of m. So this dominates. Theta of m dominates the code within the for loop. So the time complexity per the worst case time complexity per iteration is theta of m. So we multiply by the number of iterations. And the rest of the code above that, we can ignore them because they are of a lower asymptomatic class. Because you take theta of m plus theta of m plus theta of m again plus 2 theta of m, and then you plus all of this over here. It's obvious that the for loop time complexity will dominate. Yeah, so this is the worst case time complexity, which is better than the worst case time complexity of the naive algorithm, which takes theta of m times n. Yes. Yeah, so remember, we're just, for the worst case, we're assuming that this theta, this if statement, the first if statement here will be triggered for every single possible window. And at the last window, we'll also trigger the first if statement over here. And for every time we call equal string, it will take theta of n, which means you will compare every single character between P and that particular window in T. So let's say for the first window, when we're comparing P and the first window in T, we'll compare M characters. And then at the nth character, we realize that they don't match, which is why we proceed to the second window in T. And this repeats all the way until the last window in T, where we'll compare P with every single character in the last window in T. And then from there, if it has two possibilities. Either it matches at the last character or it doesn't. Yeah, but either way, it still cause the worksheet transformability to be as such. Okay, but I just want to caveat this by saying that let me just put this in reality, the average, aka the expected running time, is O of m plus m plus the time required to process spurious hits. And remember, spurious hits is holes along where HP is equals to HT, but both string are not equal in value, which I explained earlier in the slides. I think, let's see. Yeah, I explained it over here. So we see that both of them have the same hash value of HP and HT, but the actual value of small p is 5 and the actual value of small t is 18, so they don't match. So this is a spurious hit. Yeah, and why is it O plus M? Because we separated the time required to process the spurious hits. Because we add the time required to process the spurious hit separately. Yeah, so remember what I wrote over here, plus the time required to process spurious hits, which is normally negligible in a sense, which is why we decided to separate them. So over here, it will take O of m time for the two hash throws plus O of n plus O of m is equals to O2 of n, which is equals to O of m, and close to O n time on the for loop, because we don't, because we exclude the time required to process spurious hits and include it later on and stick by adding it to OM plus M. Yeah, so initially is O of n for the for loop. So if we look over here, yeah, I mean it's quite difficult to tell. I think that there will be, it's either we run it using some Python simulation code, or basically the consensus is that you take O of n time for the for loop over here. And in this case, neither O of m nor O of n dominates, which is why we include both to get O of n plus n. And then last thing is the number of spurious hits. can be low by using a large prime number Q for the hash functions. Oh yeah, actually I just realized the reason why is O of n over here for the for loop is because if we ignore the events of spurious hits which rarely occur in the average case, then it will not be theta of m over here, it will be theta of 1. That's the dominating term. So the number of iterations is m minus m plus 1 multiplied by O of 1, which is equals to O of n minus m plus 1, which can be simplified to O of n, since in real life n is greater than m. Yeah, so I'll just paste a explanation over here. This case. Okay. Is this big enough? Okay, this is quite actually piece of text, but we're about to end. Yeah, we'll just finish this in 5 more minutes. Okay, let me see whether I can paste this. So our first point over here is this. Then this is our second point. And this is our third point. You know. Oh man. Let me just tidy this up. Over here. Where is this the third point? So E as E here means SE tube. Oh my god. Okay, maybe I will just paste this in the next slide. Oh my god. My computer is lagging now. So we swipe the previous slide. Okay. So this is just a summary of the previous slides. Yeah, so I just read this out. So we expand to the previous slide. Our first point says that the worst case time complexity is this theta of n minus m plus 1 times m, which occurs when we assume that for every for loop we trigger the first if and we satisfy hp equals to ht every single time and execute the equal string function but fail at the last pair of character every time, such that we can't return and have to keep running the loop. So this is one scenario. The other scenario is we also trigger the first if every single time and we execute the equal string function for every single time, but we manage to fulfill this equal string condition to be equals to true at the very last window. So these are the two cases where it will cause this worst case time complexity over here. Okay, the second point is for the average time complexity, where we can ignore or which is we put aside first. Put aside the time taken to execute the equal string function. Since in real life we rarely use it because remember that actually due to Q being a large prime which reduces spurious hits. Yeah, so we'll rarely activate the first if statement because of because of Q being a large prime number. So that means our for loop would take let's choose the number of iterations. Yeah, so in the average case, we can't really say that the number of okay, let me just put this over here. So that means our for loop takes it is this number of iterations and the worst case per iteration. Actually, this is just the time complexity per iteration. Yeah, so it's equals to this, but shall be simplified to this since it will have n is much greater than m. But I want to tell you that this is very likely, actually no, I'll say it's incorrect logic, but I use it as it helps me to easily remember the average time complexity. Okay, so this logic over here isn't entirely accurate. It's not entirely accurate, but I just use it because it's easier for me to remember. Yeah, so I mean, there are times when like the explanation isn't 100% correct, but I will still use it because it's a lot. At least it helps me to remember the time complexity more easily. Actually, you know what? Trash that. I think it's better not to include this. Yeah, so we say it as average TC was to m plus m plus time required to process spurious is, which is negligible. Yeah, I think this is better. And how to exactly get this O m plus n? I think most of the time you can just run the Python code and run through many simulations. Yeah, for this one, I'm not too sure how they exactly got it, but I do know that in this case, it will take O n time for the first two hash throws. I'm not too sure why it will take O of n time for the for loop. I don't think it's possible to just derive it from the code directly like this. In this case, maybe I think you need to use some expectation and probability. Yeah, but I don't think this will really be tested, so we don't really need to dive deep into that. Yeah, but the average time complexity is, in this case, with this. Yeah, let me think. For the average PC, okay, let me just tidy this up. Okay. Plus m. Okay, so remember that we have the two hash function calls, which will take O of m. Okay. And then yeah, so we add 8 to the t time complexity for the for loop, which is O of n. So O of m plus O of n is equals to O of m plus n. Yeah, so this is the logic. Now, apologies if it's not too clear, but I think I just tried to explain everything in one go in the sense. And I think this is thorough enough for the exams. If I made any mistakes, do let me know as well. Thank you for watching, and the next time we'll talk about the Boyle-Moore algorithm, which is the most complex one. But not really because it's hard to understand, but rather it's because it's very long-winded in my opinion. Okay, that's all. Thank you.